In this video, I'll show you how to integrate using inverse trigonometric substitution. This is question 1. Now we all know how to integrate a function like this, where you simply perform a u-substitution with 4 minus x squared, and you end up with a function that's easily integratable. But how about a function that looks like this? Sure, they look identical, except this one has a 1 at the top, and this one has an x at the top. This one is a lot more complicated than this one. You need to use a whole different technique to integrate this, and the technique is referred to as inverse substitution. To perform inverse substitution, you need to follow this chart. Now notice that in our function, we have 4 minus x squared. This matches the expression right here, where in our case, our a value would be a 2, because only with a 2, when you square it, you end up with a 4. And since this matches our function, we have to set x equal to a, which is 2, sine theta. Here's what I mean. So set x equal to 2 sine theta. Now just a quick note, this technique works well for questions involving root signs. The idea is that since some trigonometric identities involve squares, the square will eventually cancel the root. Here's what I mean. So once you've set your x, you find the derivative of both sides. So we have dx is equal to 2 cosine theta d theta. What I did there was I took the derivative of 2 sine theta, and that happens to be 2 cosine theta d theta. The next step is to substitute my x and my dx into my function. So I end up with the integral of 1 over the square root of 4 minus, I'm going to put this in brackets here, 2 sine theta squared. I'm going to replace my dx with 2 cosine theta d theta. Now, of course, I can rewrite this function so that this is at the top. And there's my brand new function. Now what I'll do is distribute this 2 to this 2 and to this sine, where I end up with 2 cosine theta d theta over the square root of 4 minus 4 sine squared theta. What I'll do next is factor out a 4 from this radicand, where we have 2 cosine theta, that part hasn't changed at all, over the square root 4 bracket 1 minus sine squared theta. And now what I can do is distribute this radical to this 4 exclusively and to this 1 minus sine squared theta, and here's what happens. The integral of 2 cosine theta d theta, that part hasn't changed still. And the square root of 4 is 2, and the square root of 1 minus sine squared theta. Now, I made a mention up here, and I haven't discussed it yet, but some useful identities really help with these types of problems. Notice the first one, sine squared theta plus cosine squared theta is equal to 1, and we're going to use that now. Cosine squared theta is equal to 1 minus sine squared theta. So I will replace cosine squared theta with this part, and if I do that, I end up with the square root of cosine squared theta. This part right here now becomes simply cosine theta, right? Because you're square rooting a square. And we have the expression 2, which can be canceled out with that 2. And this becomes simply cosine theta, which can also be canceled out with the cosine at the top. And now you have the expression, the integral of d theta. That function is very easy to integrate. We're technically being asked to integrate the number 1. Well, let's do that. The integral of 1 is theta plus c. Now, of course, our original equation was in terms of x. So what we have to do is analyze this part. Remember, we set x equal to 2 sine theta. So we set x equal to 2 sine theta. And we can isolate for theta here and substitute it back into theta. How do we do that? Well, I'm going to divide both sides by 2, where I end up with sine theta is equal to x over 2. I'll take the inverse sine of both sides, is equal to theta, and I'll substitute this where that theta is, and we have our integral in terms of x. And there you have it. This right here represents the integral of this function. Make sure you watch question 2 of this series where we tackle another problem that's even more difficult than this one.